Hi guys. So what we're going to be doing today is we're going to be looking at trig substitution. So trig substitution is one of the, I'll say more challenging topics in a Calculus 2 class. There's a lot of similarity in the problems, but each problem tends to be quite long, and you need a lot of trig identities and stuff to do them. So it is what it is, but we'll get through it and you'll see how it goes. So before we get started, I want to show you a couple of things that aren't trig substitution, just to make sure we're all on the same page here. So when we do trig substitution, we're going to have to draw some triangles at the end. I'm going to say draw some triangles. So we're going to be doing substitutions like this. So imagine I just gave you a relationship here between a couple of variables. I say imagine x is, let's say, 3 sine theta. Okay? Now we're going to have a substitution like this. And what we want to do is we want to be able to draw a triangle that corresponds to that. Okay? What triangle would give me this? Okay? And there's a specific way you go about it, right? So you start out and you say x is 3 sine theta. Divide both sides by 3. Ooh. I don't know why that got bigger. X over 3 is sine theta. All right. Now, what you have to do is you have to remember which sides of the triangle give you which trig function. If you can remember that, like SOHCAHTOA type thing, right? Remember SOHCAHTOA, right? Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. Tangent theta is opposite over adjacent, and so on, right? The other three are these three upside down. And so you need to be able to draw the triangle that matches x over 3 equals sine theta. So what you do is, from SOHCAHTOA, basically, you know that the sine is the opposite side over the hypotenuse. So I'm just going to write that right here, opposite over hypotenuse. But what we're going to do, Englishing hard. What we're going to do is x is going to be the opposite side of our triangle, and 3 is going to be the hypotenuse of our triangle. So we just draw a triangle. Oh, that doesn't look like a right angle. I'm going to fix it. Stop it. Oh, that makes me sad. I'm gonna erase them both. We're gonna make it happen, guys. I don't know if I did. Oh well. Okay, pretend. Okay, that's a right triangle. It may or may not be, but it is. So there's a triangle. So what are we gonna do? We're gonna do what I said. X is the opposite side. So this is the opposite side, label it x. The hypotenuse is supposed to be 3. So label the hypotenuse 3. Now the third side, you have to be able to calculate. Now, it is easy enough just to guess at what the third side is if you've done a few of these. But if you haven't, then you can always fall back on using the Pythagorean theorem here. So you just write a squared plus b squared equals c squared. Plug in the stuff in the right place. The stuff means the 3 and the x. So x can be b and 3 could be c. Make sure you get the hypotenuse in the right place, otherwise you'll get the wrong answer here. A squared plus x squared is 9. Move the x squared over, so you have a squared is 9 minus x squared. And so a is going to be square root 9 minus x squared. Square root 9 minus x squared. And there you go. That's the triangle that corresponds to x equals 3 sine theta. So from that, you would be able to write down any of the trig functions that you wanted, right? You'd be able to write down all 6, right? Because if you want sine theta, well, sine theta is actually really easy because that's the one we already had, right? X over 3. Cosine theta, well, you know that that's the adjacent side over the hypotenuse on your triangle. So the adjacent side is square root 9 minus x squared. Hypotenuse is 3. Tangent theta is the opposite over the adjacent. So that is x over square root 9 minus x squared. I'm not going to rationalize that. I'm way too lazy. Just leave it that way. What else do we have? We have a secant, cosecant. Let's do cosecant. Cosecant is 1 over the sine. So 3 over x. Secant theta is 1 over the cosine. So 3 over square root 9 minus x squared. Again, I'm not rationalizing it. And cotangent theta is 1 over the tangent. So it's square root 9 minus x squared over x. Right? So you can write down all 6 of them. Not only that, but another thing you're going to have to do is you're going to have to write down what theta is sometimes on these. Okay? So the last thing you want, one last thing, if you have sine theta equals x over 3, and then you apply a sine inverse to both sides, I'm going to have to rewrite this to give myself more room. If you apply a sine inverse on both sides, then what happens is on the right, nothing happens. So you're just sine inverse x over 3. On the left, the sine inverse and the sine cancel and just leave you with theta. So from this triangle here, you get all 6 trig functions. Why can't I move that in? Why won't you let me just move it in? Why does it have to be a square? Okay, well. I'm redrawing it then, and you better work right this time. It won't. It literally won't let me just change it to a different shape. That's insane. Okay. And it also gets you this. Okay? And so you basically need to be able to do that on any problem. Both the inverse thing and getting any of the trig functions. Just starting with one thing like this. Okay? So that is a necessary skill. You do a couple of them and you'll be able to work it out. Okay? Now, the next thing I want to mention is something about signs, plus and minuses here. A note about signs. This kind of sign, plus and minus signs. Plus and minus signs. Okay? Here's the thing. We are often on these problems going to have something that looks like this. A square root of, let's say, a cosine squared x. It'll be a theta, but that completely doesn't matter. You'll have something like this, okay? And that's kind of a problem. What you need to know is that if you take a number like 5 and you square it, and then you square root it, what happens? You get 5, right? That's easy. But if you take a negative number like -5 and you square it and then square root it, what do you get? You get 5, not -5, right? Because -5 squared is +25, and the square root of +25 is 5. So you don't get a negative there. So really, when you do this, any kind of square root of a squared, you probably in your head thought that like they cancel, but they don't. What they give you is an absolute value, right? Whatever it is, it's positive now after you square it and square root it. So technically over here on this cosine, if you take a cosine and square it and square root it, you should have an absolute value of the cosine, okay? Now in our problems, we're gonna have this happen, and we don't want those absolute values. So way back at the beginning of the problem, we are going to limit our theta values, and we'll just say something like this. Like we'll say something like this, for example, we'll say, like, let x equal sine theta with theta, actually I'll say it like this, with, no, that's wrong, with negative pi over 2 less than theta less than pi over 2. They'll say something like this, and you'll be going, oh, well, why are we doing that? Why do we have negative pi over 2 to positive pi over 2? Well, the reason we have negative pi over 2 to positive pi over 2 is because on the unit circle, like that, that is this section right here, right? Pi over 2 is straight up, negative pi over 2 is straight down, and that section of the unit circle on that half, cosine theta is positive or 0. So the restriction was for theta, the substitution was for sine theta, but on that half, cosine theta happened to be greater than 0. And what that means is, up here, when you have the cosine theta, we're not going to have those absolute values because it's already positive. So if it's already positive, we don't need to write them, right? Because the absolute value of a positive number is just a positive number. Now, the reason I'm talking about it now before we do a problem is because you basically don't need to worry about this, okay? Like, I may or may not write it in problems, but I'll say 90% of the time, if you look at somebody else's work for doing a trig substitution problem, they are not going to write that, okay? It's not really necessary because there's some region you could restrict the theta for that would allow you to not have the absolute values, and you know, we can just assume that we already, like, we can just assume that we did that, and so we don't have to worry about it anymore, okay? And so it's kind of something that you can worry about and nobody really does worry about, and we won't, okay? But that's why, because we don't want to write those absolute values, so we want to do something. Okay, we're almost ready to start, but we have one more thing. Yeah, I can't fit it up there. So recall this. Recall some of your trig derivatives or trig integrals, inverse trig derivatives or trig integrals. Maybe I'll write them this way. I'll write them derivatives, it doesn't matter. We could write them as integrals, but the derivative of sine inverse is 1 over square root 1 minus x squared, okay? And what I want you to pay attention to is that, okay? Now, we also have the derivative of, let's say, tangent inverse. That one is 1 over square root 1 plus x squared. Again, I want you to pay attention to that. And then we have the derivative of secant inverse x. That one is more complicated, but 1 over absolute value x square root x squared minus 1. And I want you to pay attention to that. And so look at what we have there. Those three things have, they all have a different form, right? Like whether it's a plus or minus is different. And on the two top, or sorry, the top one and the bottom one, one of them is 1 minus x squared, and one of them is one of them is x squared minus 1, right? So you could tell them apart just from the part that I highlighted, okay? And that's important because you can relate those things, like when you see 1 minus x squared, that could make you think of a sine inverse. And when you see 1 plus x squared, that could make you think of a tangent inverse. And when you see x squared minus 1, that could make you think of a secant inverse. Okay, and we learned these in the section on inverse trig derivatives. But you should remember it right now because it helps you decide on the substitution. So now we can actually start to finally talk about trig substitution. Trig sub. Okay, so what we're going to do is you can try trig sub when you have one of these in your integral. So if you have an a squared minus x squared, that's one thing. If you have a squared plus x squared, that's another thing. And if you have x squared minus a squared, that's another thing. And specifically, what you want to do here is, in the first case, a squared minus x squared, the substitution you want is x equals a sine theta. And the reason you would know that that's a sine, well, one, I'm writing it right here, but the way you could have known is that when you see the a squared minus x squared, that looks like this right here, right? The only one that had a constant minus the x squared was the sine inverse, not the tangent or secant. And so that's how you can keep it apart here. It's the same pattern. Now this is going to be a substitution that we use. So there's going to be an x and there's also going to be a dx. You get the dx in the usual way, you're going to take a derivative. So the derivative of a sine theta is a cosine theta d theta. And then for the next one, a squared plus x squared, well, that looks like the tangent one, right? That's the one with the plus. So we'll be using x equals a tan theta, and dx is going to be a secant squared theta d theta, right? The derivative of tangent is secant squared. Last one, x squared minus a squared, that is going to be a secant substitution. So a secant theta. And the dx then would be a secant theta, tangent theta, d theta. Now, for each of these, like I said, there was an interval that you were supposed to use for the theta. And, I could write it. I could write it, so let's write it. So let me just think for a second. By think, I mean read. That piece of paper has nothing written on it. That's not the one I want. I could have sworn I wrote something on something. Life is hard, guys. You think you're on top of things, and then you lose a piece of paper. All right, there it is. Wrote something. So a sine theta. So for sine theta, you want the one that I actually already said, right? You want theta in negative pi over 2 to positive pi over 2. And for tangent, you also want negative pi over 2 to positive pi over 2. And for secant, it's actually different. You want theta between 0 and pi over 2, or pi over 2 to pi. And I wrote that a little bit wrong because we can't have pi over 2 because pi over 2 will not be defined. And so anyway, those intervals that I'm putting there are not something that you have to think about. You don't have to write them, really. They're just there to, I don't know, make it better from a theoretical standpoint. But there we go. So those are the substitutions. Okay. Now you want to be careful. You don't want to apply trig substitution when you don't have to. Okay, be careful. You wouldn't use trig sub if a regular sub will work. Right? So like example, like if you have this integral where I say 2x over 1 minus x squared dx, that has a 1 minus x squared, which looks like what we have for a sine substitution. But a sine substitution is unnecessary because you can just do a simple u sub with u equals 1 minus x squared, du equals 2x dx, and when you substitute that in, you get very easily just a du over u, which is, you know, an ln absolute value of u, and, you know, so on. I guess I only skipped one line of work, but that's the point. The point is that you don't want to do a trig sub here. Now, a trig sub will work. It will work just fine. It will, however, not be on one line. It'll be like on one full page of work. Okay? And so, you know, be careful when you're applying this outside of this section. I mean, in this section, you probably just have trig substitution integrals to work with. Okay, so let me find a trig substitution integral here that's not too hard. Okay. Oh man, that's rough. All right, let's try this one. So here's the one we're gonna try. So this is our first actual example here. So we're gonna integrate the integral of 9. I'm gonna write the 9 on the outside even though they don't. Square root 4 minus x squared dx. Okay? Now, again, you should not try trig substitution right away. You should think if it's an easier integral. But in this case, it's not. We have to use trig sub, so we're going to. But you should at least consider the possibility that you don't need it. Okay. But you do. So this is the integral of 4 minus x squared, square root. So 4 minus x squared. So you look back up here, and that looks like this, right? 4 minus x squared. So when you have 4 minus x squared, then obviously the a squared is the 4, right? So what's a then? A would be 2, right? Because if a squared is 4, you actually need the square root to get the a. So the a here is actually square root of 4. So you have to know that. And then what we're going to have for our substitution is going to be x equals a, which is 2 sine theta. And then the dx, you take the derivative, is 2 cosine theta d theta. All right. Now, once you have that, you substitute it in the way that you would for any substitution. So you just substitute in. Okay, so you have 9 integral square root 4 minus x squared. Make sure you treat any x like it's in parentheses. So parentheses 2 sine theta squared. And then you've got your dx on the outside, and the dx is actually 2 cosine theta d theta. So that's a very kind of significant thing, right? if you screw up and you don't substitute in for dx, then you'll mess this whole thing up. Okay, it just won't work at all. Right? So weird there. Now I can take the 2 and the 9, combine them, so get 18 integral square root. And I'm going to go ahead and square this, the 2 sine theta. So you square it, you get 4 minus 4 sine squared theta. And then on the outside we have cosine theta d theta. So like what we did so far, you do on every trig sub problem, right? All of this is just kind of on autopilot once you've done a couple of these. Now something else you need to know is you'll notice that the 4 ended up there and there, 2 places. That must happen. If that doesn't happen, you already screwed up. Okay? If these numbers don't match, you made a mistake. Okay, you're always going to get to this point. Now, what you're going to do now is also something that happens in every trig problem. You're going to apply a trig identity. You're going to need one of these identities. Let me actually rewrite it one more time and then I'll write the identity. So you can, a lot of times you won't, but you can, since that number is the same, you can factor it out like that. And now you'll need a trig identity. So the trig identity you're going to need for every single sign substitution problem, right? It's going to be the same in every one of these. The trig identity you're going to need is this one. 1 minus sine squared theta is cosine squared theta. And that's just from sine squared plus cosine squared equals 1, just with one of the trig functions moved to the other side. Okay, so you need this identity. So again, every single sign substitution is going to do the lines of work that we just did. And now we're going to make the substitution for 1 minus sine squared theta. So we're going to have 18 integral square root 4. But now, instead of 1 minus sine squared theta, we're going to have cosine squared theta. All right, and then we have another cosine theta d theta on the outside. Now what? Well, now what we need to do is take the square root here. So we're going to take the square root. We have 18 integral. You take the square root of each of these separately. So the square root of 4 is 2, and the square root of cosine squared theta is cosine theta. Now remember what I said about that, right? It should be absolute value cosine theta. But up here at the top, I should have said 4 theta in negative pi over 2 to positive pi over 2. And then when you do this step down here, for that theta, the absolute value of cosine squared theta is actually just cosine theta. Sorry, the absolute value of cosine theta is just cosine theta because on the unit circle, we're in this section, the section over here. Okay, so it was just set up so it works. And that's why it doesn't really matter if you write it, because, you know, somebody could make it work if they wanted to. Don't have to write every last detail. Okay, so we're back here. So we took the square root. We did not use an absolute value, which means I can go ahead and combine these two cosines. Take the 2 out. We're going to get a 36 integral. Cosine times cosine is cosine squared theta d theta. Okay, so this is kind of, at this point, we're at the point where every single trig substitution problem from here on out is going to be different. Like everything we've done up till now just is the same. Okay, so from here on, every trig sub problem is different. Right? So there's a right way to do this. We're probably going to do it the right way. But what you've got here is an integral of cosine squared d theta. We just have to integrate that. It involves using trig identities a few times. Okay? If you're really pressed for time, you cheat. You look up that integral. I don't know why I'm on Wolfram Alpha. I guess I was. What I should have done is I should have grabbed our common derivatives and integrals sheet. If it's on this one, common derivatives and integrals, just to see if he happens to have the integral of cosine squared. Does he? No, he doesn't. That's sad. Okay. If he did, we would have copied it and stolen it. But he doesn't. What he does have, I think, is he'll have some help with trig sub right here, right? Look at that. He has some advice for trig substitutions. Anyway, that cheat sheet is listed on Canvas. We'll just go ahead and do it. It's not going to be a big deal. We'll do the integral. So back here, let's do it. I have to actually close the note program and then open the note program, or my battery will die. All right, so from here on, every trig sub problem is different. We need an identity for this one. So what we're gonna have to use is the identity, use the cosine squared theta is what? So I think it's 1/2, 1 plus cosine 2 theta. That should be right. It's either plus or minus. If I knew my trig identities, I would not have any trouble with this. Just gonna double check it just so I don't get the sign wrong for you. So many papers, man. Yeah, okay, of course. Sometimes I just don't trust my brain to be telling me the right thing. Okay, so let's use that identity there. So we have 36 integral 1/2 parentheses 1 plus cosine 2 theta d theta. You know, take the 1/2 out with the 36, have an 18. And we have 1 plus cosine 2 theta d theta. Now this is an easy integral. So you integrate this using normal integration rules. So the antiderivative of 1 d theta is going to be theta. And then the antiderivative of cosine 2 theta is going to be sine 2 theta over 2. Okay, and then we're going to have a plus c. All right. Well, there's a problem here. Like if we were just trying to integrate this, we would be essentially done. We have to go back to the original variable. Go back to x's. And there's a problem that you don't even know is a problem. Okay? So what we're going to have to do is we need to draw the triangle. And that's fine, but we're going to draw the triangle for theta, right? In the triangle that we drew way up here, we have a theta. What we don't have is a 2 theta. So even though this was a good way to integrate it, where we have a 2 theta, we can't have that because we won't be able to use our triangle. So before we do, we have one other thing we have to do. We need another identity to take care of the 2 theta, which is simply Sine 2 theta is 2 sine theta cosine theta. All right. And so let us rewrite our integral now. We have 18 parentheses theta plus 2 sine theta cosine theta, right? Because we're substituting for there, over 2 plus c. So we are now at, I'm going to go way up here, 18, is it 18? Theta, 18 theta plus, we can cancel these 2's, so I guess it's just 18 sine theta cosine theta. All right, and I feel like we're actually going to be able to write our answer here on the next line of work. That's where we're going to put it. Hopefully it'll fit. That's where we're going to put the answer, but we need to find the answer, so we're going to need to use our triangle. Okay, so where's the substitution? We need to find the substitution. It is somewhere. Here it is. X is 2 sine theta. So let's draw our triangle. X equals 2 sine theta. We need the sine theta by itself, so divide by 2. X over 2 equals sine theta. Now we know sides of the triangle that that's the opposite side over the hypotenuse, and I'm going to draw a triangle for that. So I'm going to put the opposite side as x, the hypotenuse as 2. You calculate the third side, but it's just going to be 2 squared, which is 4, minus x squared. So we're going to get that. By the way, it's a good sign when your third side looks like what you had in your original integral. So like we had an integral 4 minus x squared, and look at that, 4 minus x squared. It doesn't always happen though, so it doesn't necessarily mean anything. All right, so there's my triangle. Once we have the triangle, we can do most of this. We do need to remember what to do with, not that, what to do with this. Remember how I said you could do the sine inverse of both sides here? You can, and you're going to get sine inverse x over 2 is theta. All right, now let's write our answer. So let's come up here. So first of all, 18 theta. Well, we just came up with theta is sine inverse x over 2. So we have 18 sine inverse x over 2. Okay. Plus 18 sine theta. What's sine theta? Well, sine theta is easy. It's right here. X over 2. So 18 times x over 2 times. Then we have cosine theta. What's cosine theta? Well, cosine theta, remember, is the adjacent side over the hypotenuse. You have to know those. So adjacent hypotenuse. So it's going to be square root 4 minus x squared over 2. So square root 4 minus x squared over 2. And that's basically our answer. I guess we could write it a little nicer, so I will. We could write it as 18 sine inverse x over 2 plus, looks like 18 over 4, except that 18 over 4 is 9 over 2. And then we just have x square root 4 minus x squared and then plus c. And that will be my answer. Wow, so take a look. That's a lot of work, right? A lot of work. But remember, like everything up here, this is all kind of the same on every problem. Everything is always the same until this point. And at this point, you just have to integrate whatever you have. And so in this case, we had an integral of cosine squared, and that integral is a little bit more trouble than some of the other integrals. So that is, why it came up the way that it came. All right, let us do a different one. How bad is that going to be? I think that's going to be fine. Let's try that one. Oh no, because that's another sine substitution. I want to do a different one. We need to do like a tangent or a secant. Man, they really like the problem that we just did. Really like it. Just saw it 3 times in a row. Okay, here we go. Here's a different one. All right, new problem. So our new problem is going to be integral dx over square root 196 plus x squared. Is 196 a perfect square? What's the square root of 196? Where's a calculator? How do I not have a calculator? I own like 30 calculators. All right. 196 inter square root 14. Okay, cool. I had no idea. All right. So here's an integral. You try to think about how to do it. It's almost an inverse tangent, right? Like if it was like this, it would be an inverse tangent, but it's not. It has the square root. So it doesn't match what we know. You can't use a regular substitution. If you try, you will fail. And so what you've got to do is trig sub. So the a squared is 196. So a is the square root of 196, which I just did, and it's 14, which is good. It's nice that it's a good number. It doesn't really matter though. So what are we going to do with that? Well, we're going to pick our substitution. Now we have a plus sign here, and if you look at your possible substitutions, the one with the plus sign is a tangent. So x should be a tangent theta. So your substitution is let x equal a, which is 14, tangent theta. That makes your dx 14 secant squared theta d theta. Now what's the range for theta? Who cares? Who cares? I'm not even going to write it. I refuse. I can scroll up and look at it. I could even tell you what it is now because I happen to know it, but I'm not going to. All right? We don't care. Somebody worked it out, or somebody could work it out if they wanted to. All right. So there's our substitution. So substitute it in already. So we got integral dx. Don't forget to substitute in your dx. It's the biggest mistake people make. So 14 secant squared theta d theta. That's your dx. In denominator, we've got 196 plus x squared, which is 14 tan theta squared, which will take us up here. So what will we get? So we have an integral. On top, 14 secant squared theta d theta. On bottom, we're going to get 196 plus 196 tangent squared theta. Now, what do you think we're going to do here in the denominator for this? Okay. What did we do last time? Last time we had, where is it? Last time we had this, right? And then magically there was a trig identity that applied. Well, guess what? There is always going to be a trig identity that applies. The reason a trig identity is going to apply to this is because that's the entire reason why we used a tangent. Like why is it a tangent and not a secant or a sine? Because we want an identity to work, okay? So even though you have already seen on numerous occasions that I cannot remember trig identities, I know what the trig identity is here. I know it for sure because I'll write one more thing and then I'll write it. I was on a roll too. Factor out the 196 and you have 1 plus tangent squared theta. Now normally it's hard to remember like how the signs will work out on all your trig identities and stuff, but I know that this one has to be 1 plus tangent squared theta equals secant squared theta. That's an identity. I know that's got to be right because it's got to match what I have. So it's got to be 1 plus tangent squared theta. And I know tangents and secants go together, so I'm not worried about that part. So we apply our identity. The reason I'm making a big deal out of that is because you shouldn't have to look up a trig identity at that point. You should just understand that there is one, and if you know that there is one, you should be able to figure out which one, like what it would be. All right, so we apply our identity, we get here. So then we have to square root this. So 14 secant squared theta d theta. On the denominator, we're gonna factor, we're going to square root. Square root 196 is 14. Square root secant squared is absolute value secant, except we're just writing secant and hoping nobody catches us. So we have that. Then what you're going to do is simplify, right? This is the point where, now we diverge from the previous problem, right? Diverge from previous. This is where they go in different directions. Okay, so what we need to do here, I can cancel a 14, I see that. And also I can cancel a secant theta with one of the secants in the numerator. And so what I'll end up with is a pretty simple, it looks like, just the integral of, is it just a secant? Is it just a secant theta? That's nice. Okay, so it's just a secant theta. Now then you have to remember, what is the antiderivative of secant theta? We did that in the section on logarithms. So let us go back to our, what's it called? Common derivatives and integrals, and you can definitely look up that one, right? It's right here, real big. Secant theta, ln secant u plus tangent u. Well, for us, theta. So ln secant plus tangent. That's good. We don't have to remember it. We just have to write it down. So this one is quite simply ln absolute value secant theta plus tangent theta plus c. That's easy. Now again, notice how much less work that was than the previous one, right? Sometimes you get lucky, sometimes you don't. So the cosine squared was a tougher integral than secant, because secant we just look it up. All right, now what? Triangle, right? We don't need any extra trig integrals, nothing. We just need the triangle. So we need to know our substitution. So what was it? It was x equals 14 tan theta. There it is. So x over 14 is tan theta. What sides of the triangle is that? Look it up. Opposite, not hypotenuse, that's sine. Opposite and adjacent. Okay. So you draw your little triangle, or big triangle, whatever size triangle you like. And then we've got opposite side is x. There it is. Adjacent side is 14. There it is. You have to calculate the third side. Again, you should be getting better at this to where you don't need to like use a calculator here. Or I mean, you don't need to use the Pythagorean Theorem. So there's only two things that can happen for the triangle. Basically, if what you're missing, so we were missing this side on the previous one. If what you're missing is like one of the short sides, like the A or the B, then all you're doing is it's the square root of, right? This is square root hypotenuse squared minus the other side squared. And if you were missing the hypotenuse, then the only difference is that you would have a plus. So without thinking, I just say, oh, well, what is this? It's 14 squared plus x squared. So if it's the hypotenuse, you put a plus, and if it's one of the others, you use a minus. So again, I'm not thinking too hard about that. So there it is. We know that 14 squared is 196 now too, so keep that in mind. So then we come back here, natural log, absolute value, secant theta. What's a secant? Secant is going to be hypotenuse over adjacent. Yeah, because it's upside down cosine. So hypotenuse over adjacent. So we have square root 196 plus x squared over 14 plus a tangent. A tangent is going to be opposite over adjacent, which is this one and this one. So x over 14 plus c. And that's it. That's your answer. All right. So that was probably a little bit easier for you than the previous one. And, you know, you just get what you get. Once you get it down to a single integral, like this point, you know, you can go and check it on like Wolfram or something like that if you're confident in your trig substitution work. And you just want to make sure that you did the integral right at the end. Okay. Let's see here. All right. So one thing we need to do is there's kind of an extra thing here. And I need to find a specific one. Okay, there we go. Here's one. All right. So one extra thing. What's the one extra thing? It's completing the square. All right. So forget integrals for a second. This is an algebra technique. So, you know, you can learn it in high school. You probably did. You probably forgot it. I'm going to show you right now how to complete the square. So let's say you have something like this. X squared plus 10x. All right. And let me do even one more thing here. Let's say x squared plus 10x plus 1. Now, if you were trying to factor this, it would not factor. It doesn't factor. You can try. It doesn't. At least I hope it doesn't, because I don't want it to. Right? It doesn't factor. Okay? But you can complete the square. What is completing the square? Completing the square is when you do this. You take this middle number right here, the number on the x. You take that number, you divide it by 2, and then you square it. Okay, so 10 over 2 is 5. 5 squared is 25. Okay, now what this is this is like a magic number. It doesn't have a name. Nobody calls it the magic number but me. Did you see what I just did? I just put a K on magic. Incredibly embarrassed about that. But it happened. You saw it. All right. So you get the magic number. And what you're going to do with that magic number is this. So you take your x squared plus 10x, and you take that magic number, and you go plus 25 minus 25. You just put it right there. And then also, don't forget about this number on the end. That one still exists, so it's right there. Okay? Now, the reason you add and subtract that number there is because you're not trying to change anything, right? If you add 25 and you subtract 25, then you haven't really done anything. That's what we wanted. So you do that, then you just throw some parentheses around there, the first three terms. Now, why are we going to do that? Because the part that I put parentheses around does factor. This factors. All right? So that's going to factor. What's it going to factor into? Well, it's going to factor into x plus 5 squared. Now, by the way, the 5 there is not arbitrary. It's half of this middle number, right? It is the number that is inside here. Okay? It's also the square root of this number. So you shouldn't have to think very hard about what it factors into. Like the square root of 25 there is 5. So x plus 5 squared. But that's only the first three terms. What about this nonsense over here? What happens with this? Why won't you let me pick a color? Okay. What happens with this? Well, you just have to carry that through. So negative 25 plus 1 is negative 24. Okay? Now, why do you care about this? Right? Why do you care about being able to write x squared plus 10x plus 1 and being able to write it like this? Because that's all we're doing is we're writing it in a different way. Okay? The reason we care is because completing the square lets you force a problem into matching the trig substitution pattern. Okay? We can complete the square to force certain problems. Trying to write certain, can't do it. Certain problems into matching the pattern of trig substitution. Okay, that's why we care. So an example of this, and here's an example from the homework. It doesn't actually make us do the whole integral. It just makes us do the completing the square and substitution part. So wow, that's what I'll do. I'll say, they say, the way they say it is weird. They say which expression can be used to solve, and then they give us this integral square root x squared plus 4x dx. Okay, and so the thing is that if the x wasn't here, like this looks like trig substitution. You put the x back, it doesn't look like trig substitution anymore, right? We didn't have an x squared plus ax. We only had x squared plus a squared. Okay, so this does not match the way it is. And so what you do is you want to force it to match the pattern for trig sub. So what you have to do with this x here, which is a problem, is we need to complete the square. Okay, x bad, complete square. That's how a caveman would say it if a caveman was completing the square. X bad, complete square. X squared plus 4x. We need a magic number to add. Okay, how do you get the magic number? You take the middle number, the 4, you divide it by 2, and then you square it. So 4 over 2 is 2, 2 squared is 4. So the magic number is 4. So you just take this and you just go plus 4 minus 4, like that. Once you have that, throw some parentheses around here, like that. And then we factor the part in parentheses. So what is x squared plus 4x plus 4 going to factor into? It's going to factor into x plus 2 quantity squared, right? x plus 2 quantity squared, and then you have this extra minus 4. All right, that's the completing the square part. Now what you're going to do with that is that your integral is the integral of square root, well, we just replaced it. It's going to be now x plus 2 quantity squared minus 4. Okay? Now you might think, well, that still doesn't look like trig substitution, right? It doesn't look like trig substitution because on trig substitution, like I fixed, what did I fix? Like I fixed the a squared part. Like we've got one of these now, or one of these, or one of these, whichever one it is. We have one of them. But we kind of messed up the x squared part, right? Well, yeah, we kind of did, but what you can do is, we didn't talk about it, but that's why we're talking about it now. What you can do is if you had, for example, instead of a squared minus 4, like let's say you had like 9 minus, and then here you wrote x plus 3 squared, right? That looks basically like this. It's just that we have an x plus 3 instead of an x. All you would have to do in your substitution is when you're making the substitution here, you would just say, well, a sine theta is 3 sine theta. That part is fine. But instead of an x, we have x plus 3. So that's it. That's all you have to do. If you have x plus 3 where the x should be, then in your substitution you put x plus 3 where the x should be. It's not that hard. So let's come down here and see what we have. No idea. Okay, x plus 2 minus 4, right? So if it was this, right? If it was, in a better color, if it was x squared minus 4, we would use, it would be a secant, and it would be x equals 2 secant theta. That's what we would use, right? But it's not. Since it's x plus 2 squared minus 4, we're just going to use x plus 2 equals 2 secant theta. All right, so that's all you have to do there to make it work. So we go x plus 2 equals 2 secant theta. So you take your derivative of both sides. The derivative on the left is still going to be dx. That doesn't really change. The derivative on the right is going to be 2 secant theta tangent theta d theta. And then you substitute this in and you'll see it works out okay. So we're going to have integral square root x plus 2 is 2 secant theta, right? So all of this gets replaced with this. So you have parentheses 2 secant theta squared minus 4. And then your dx, which is 2 secant theta tangent theta d theta, which is integral 4 secant squared theta minus 4, 2 secant theta tangent theta d theta. All right, let's keep going. What are we going to do here? Hopefully you remember by now, we are going to apply a trig identity. Specifically, what do you think secant squared theta minus 1 is? Remember what I said about this a couple of times now. The trig identity will apply. So I know that the signs are right and all that. And then which two trig functions go together? Secant and tangent. So secant squared theta minus 1 must be tangent squared. And I'm not really thinking about whether the signs are right, I just know that they'll work out. So I get integral square root. I'm not factoring out the 4 this time. I know I'm just going to have the 4 there. And then tangent theta squared. And then 2 secant theta tangent theta d theta. Let's square root this. You square root the 4, you get 2. You square root tangent squared, you get tangent. Again, technically you don't, but we are not caring. So you get all this. Then what do we get? We have a 2 and a 2. That's a 4. Integral. Then we have a tangent and a tangent. That's a tangent squared theta. And then we have a secant theta. And then we have a d theta. All right. Now, this is a hard integral. Right? This is a very long integral to do. They don't make you do it right here in the homework. What they do is they make you pick this off a list of several other forms, right? They say, how did they word it? Did I word it that way? They say which expression can be used to solve. So they don't say solve. They just say what expression can be used to solve, and this is what they want. So if you integrate this, you get the answer. Okay, but we are not, because it's a very long integral and it's been 1 hour and 5 minutes. If you did want to do this, at this point, right, where you've already done a significant amount of work, I would just say, well, integral tangent squared secant, right? Let's just go Wolfram. I mean, check your common derivatives and integrals. It's very closely related to this one, by the way, secant cubed. It's not that we can't do it, it's that it's a long integral. Go here. Integrate. What was it? Tangent squared. X. Secant x. It knows what I want. It knows me so well. No, it doesn't. That's not what I wanted, Wolfram. You made me a liar. Put the cursor in the right place. Okay, it'll get it right now. All right, that's the one. All right, see why we don't want to do it? That actually looks, that's not a good way to write it. That's not a good way to write it at all. They must have a better way. Okay, well, I lied. Don't use Wolfram alpha to do that integral. That's bad. All right. Anyway, so regardless, I think we're going to be done with this. This was a long lecture, and we saw one of each kind. Although we did not finish the secant integral, we saw completing the square. And again, I'll caution you that in real life, do not try trig sub if a regular sub is going to do the job. Okay, it's going to be wasted effort. All right. So that's it for this lecture. I will see you in the next lecture.